why did we do the Euclidean algorithm in the case of integers? Well, one of the points was to try and compute the GCD of two numbers, right. So, what was the GCD? So, what in the usual case, if you remember this example again, let us go back to the usual Euclidean algorithm. So, we wrote 189 and 35, this was 5 times 35 plus 14, and then 35 divided by 14, 7, 14 finally just became 2 times 7. Okay. Now, we use this, and so we finally said, well, that just means 7 is the GCD. So, 7 happened to be the GCD of these numbers. And so, we could rewrite 7 back in terms of the two numbers 189 and 35. That was a very important consequence of the Euclidean algorithm. So, observe that we can sort of work backwards. So, from the first step we write the remainder 14 in terms of the original numbers. So, it is 189 minus 5 times 35. Okay. Now, from the second step we can write the remainder 7 as again in terms of 35 and 14 as 35 minus 2 times 14, but we substitute 14 back in terms of 189 and 35. So, the point of this finally is that 7 can be written as follows, it is minus 2 times 189. So, I have written it as minus 2 times 189 plus some multiple of 35, right. What multiple of 35? Minus 2 into minus 5 is 10 plus 1 on the outside, 11 times 35. So, I have written it as minus 2 into 189 plus 11 times 35. In other words, I have written it as some a times 189 plus b times 35, where a and b are integers. Okay. So, this was one of our main consequences of the Euclidean algorithm. Now, what does that mean? Let me just rephrase it as follows. So, let's do the following. Let's consider another way of thinking about what this is. So, let's take the set S, okay, and S is constructed starting with the numbers 189 and 35. So, I will just call it S of 189, 35. Okay, it is a set which is defined as follows. Consider the set defined as the elements of the set are just all numbers, it is a set of all numbers of the form 189 times A plus 35 times B, where I let A and B vary over all integers. Okay, all integer linear combinations of 189 and 35, and the claim here is the following. So, let us also consider another set. So, let T be the following set, it is all multiples of 7. So, remember 7 was the GCD. So, I claim if you take all multiples 7 times C, as C varies over all integers. So, this is all multiples of 7, then these two sets are the same. Okay. Then, so recall in a sense, here is a rewording of what we talked about earlier. If we take 189 and 35, this set turns out to be the same as the set of all multiples of 7. Okay. And the proof, if you remember, is straightforward. So, on the one hand, we know that anything which is a linear combination of 189 and 35, any number of the form 189A plus 35B, since both 189 is divisible by 7 and 35 is divisible by 7, so is 189A plus 35B. In other words, every element of this set is automatically divisible by 7. So, every element on the left hand side is an element of the right hand side. What is less obvious is that every element of the right hand side is also there in the left hand side, and to do that we will take this special element 7, and that is the one we really have to worry about. So, to show the other way containment, we just look at the element 7. Now, consider 7, that is an element of T, of course. I claim it is also an element of S of 189, 35. Why? Because of Euclidean algorithm. We just said 7 can be written as minus 2 times 189 plus 11 times 35. Okay. So, what this means is that this is some 189A plus 35b for a equals minus 2 and b equals 11. So, of course, this belongs to the set 189, 35. Okay. Now, if 7 belongs, then any multiple of 7 automatically belongs, because now if I just take 7 times c, then it is just I just put minus 2c and 11c into 35. Okay. So, of course, that's still a multiple of, that's still an element in the set S. Okay. So, therefore, I have proved that every element of T is also an element of S. So, T subset of S. So, this was in a sense the point of the Euclidean algorithm, that you can write the GCD as an integer linear combination of the two numbers. Okay. Now, the reason we are revisiting this is because now that we have thought about doing the same sort of algorithm for the numbers 1 and root 2, right. Now, what does it imply here? So, the first thing, recall that the Euclidean algorithm to 1 and root 2 does not terminate. So, you do not finally get some final stopping point where you do not produce like a GCD or anything, you just keep going on and on and on forever. Okay. So, let us consider the same sort of thing, but then with the numbers 1 and root 2. So, let us look at the set S of 1 comma root 2 or root 2 comma 1, whichever, which by definition is just the set of all numbers of the form 1 times a plus root 2 times b, where a and b now vary over integers. Okay, it is still the set of all integer linear combinations of the numbers a and b. Now, the question is, what can we say about S? What does S look like? Okay, in the earlier case, we were able to say something that S and T are the same, for example, and T was what? All multiples of 7. So, S is actually, even though it looks like I am taking linear combinations of two numbers 189 and 35, secretly it is just all multiples of 7, right, all multiples of the GCD. In particular, it means that S has a smallest positive element, right. What is the smallest positive number that lies in S? It is the number 7 itself, right. So, observe, this is true. So, in particular, this means that, so in fact, S contains a smallest positive number, real number, or well, in this case integer, which is namely the number 7. Now, what was 7 really? 7 was what you got when you kept doing the Euclidean algorithm all the way to the end, and in this case it terminated somewhere. So, that very last guy that you got in the Euclidean algorithm is in fact the smallest positive number that lies in the set S of 189 comma 35. Now, the same question here, let me ask the same question. So, in particular, let me ask a more precise question. What can we say about S? In particular, does it contain a smallest number? Is there, does S of 1 comma root 2 contain smallest positive, now in this case everything is real, smallest positive real number. Remember here it does not terminate the Euclidean algorithm. So, that already means maybe there is something funny or fishy that is going to happen. But let's just go back here and see what computation we did with 189 and 35, right. And let us just try to copy the same thing, but with 1 and root 2. Okay. So, I am just going to try and do the same thing, but now with 1 and root 2. So, what was the step that we had? Root 2 was 1 times 1 plus R1, R1 was the remainder. Now, I divided 1 by R1, got R2 as remainder. I divided R1 by R2, got R3 as remainder, and so on, right. I know what all these numbers are, R1, R2, R3. So, let us try and do what we did earlier. So, observe R1, which is the very first, from the first equation, what did we do in the 7 and 189 case? We tried to write everything in terms of the two original numbers, right. So, I will write R1 in terms of root 2 and 1 as root 2 minus 1 times 1. Okay, good. Now, I will go to the second step, I will write R2. R2 is, well, what is it? It is again I will write it in terms of 1 and root 2, it is 1 minus 2 times R1, but R1 is just root 2 minus 1 times 1. Okay. So, just like with 189 and 35. So, this just means it is 1 plus the same expressions that we had before, it is 3 minus 2 times root 2. So, it is 3 times 1 minus 2 times root 2. Okay. You could do the same thing with R3, you could also write R3 back in terms of R1 and R2, write R1 back in terms of 1 and R2, 1 and root 2, similarly R2 back in terms of 1 and root 2 and so on. But in fact, from here it's already clear we could do it more quickly. So, in general, not just R3, what can I do with Rn? Well, Rn itself I know what it is, it is root 2 minus 1 whole power n. So, I claim that the nth remainder can actually be written back in terms of the two original numbers. So, remember that was the point of doing the Euclidean algorithm, you had to sort of do it step by step. Every remainder you wrote it back in terms of the two original numbers, right. The next remainder you wrote in terms of the current dividend and the divisor, and then went back once more and so on. So, here again we are trying to do the same thing, but we actually have a shortcut available because we know a formula for the nth remainder, so root 2 minus 1 power n. So, in particular that means that I know the binomial theorem, I can write this as n choose 1 root 2 power n, n choose 2 etc. etc. So, I can write this as root 2 power n minus n choose 1 root 2 power n minus 1, n choose 2 root 2 power n minus 2 and so on. So, I actually have an expression, so plus last term is minus 1 power n. And now observe that this expression that I have written here is actually some linear combination of root 2 and root 2 and 1. So, for example, if n is even, so the two cases you need to look at if n is even or odd. If n is even, say let us write n as say 2k, then this expression here root 2 power n is just 2 power k, okay, and let us go to the next guy, plus n choose 2 root 2 power n minus 2 is just 2 power k minus 1, n choose 4 2 power k minus 2 and so on. Okay, so, those are the terms which do not have root 2's in them, and what are the terms with root 2's? So, if I take, so n by the way is 2k in this case, so it is 2k choose 2, 2k choose 4 and so on, and then the other terms 2k choose 1 root 2 power n minus 1, I can write it as 2 to the, so n is 2k, so it is 2k minus 1, so it is k minus 1, and then there is an extra root 2, okay. So, plus 2k choose 3 plus blah blah times a square root 2. Okay, so, what I have done really is written this remainder, the nth remainder Rn, as some multiple of 1. So, some a times 1, so let us call it an, plus some bn times root 2, okay, where what are an and bn? They are some integers, right. I have just used the binomial theorem, just expand power of root 2 minus 1, it nicely splits into two parts. There is one an integer part, another is some integer multiple of root 2 part. Now, I have done it for the even, so you should try doing it also for the odd case. So, here is a exercise problem for you guys, do this for n odd, okay, and again convince yourselves that what you will get again will be of the same form, okay, some multiple of 1 and some multiple of root 2. So, what does this mean? It means that even though I am doing this Euclidean algorithm with real numbers, something is still, it still works the same way, which is that the remainders that I am generating at every step, okay. So, the nth remainder for every n is actually some integer multiple of 1 plus an integer multiple of root 2. In other words, it belongs to the set of all integer linear combinations of the two original numbers for all n. Okay, so, this is the key point, this is what the Euclidean algorithm really does for us. Okay, good. So, that is the same as what we have for integers. So, now let us see what the conclusion is. So, let us go back to our question, what can we say about S? In particular, does S contain a smallest positive real number? So when I said S here, of course I meant S1 comma root 2. Now let us see what did we just realize about S. We realized that every one of these remainders actually belongs to S. Every one of the Euclidean algorithm remainders belongs to S for all n greater than or equal to 1. So what does that mean? It means in particular that, so you recall what is Rn? Rn is actually R1 power n. So remember Rn was actually root 2 minus 1 power n, or Rn R1 power n. And what can we say about these guys? Well, remember R1, which is root 2 minus 1, is a number between 0 and 1. So when I keep taking higher and higher and higher powers of this guy, what will it do? Well, its limit will just be 0. So here's 0, here's 1, here's R1, R1 squared, R1 cubed, and so on. Higher and higher powers of R1 will just converge to 0. So observe, limit n tends to infinity of Rn is actually 0. Okay. So what does that tell us? Well, it tells us that the question that we posed here, that whether S contains a smallest positive real number, well, the answer to that question is no, it does not. Right? Why? Because look at each of the Rn's, they are all elements of S, and there is no smallest positive number because the Rn's is actually a sequence of numbers which is going towards 0. So you pick any candidate number, there is some some epsilon, there is some Rn smaller than that epsilon. So there is no smallest positive real number. Okay. So that is the key difference between when you have two integers versus when you have, say, numbers like 1 and root 2, where you don't end up generating in the integer case, what happens is the set S is actually very, very nice in the sense that the possible integer linear combinations, if you try to write all integer combinations of, say, 189 and 35, it just has this sort of very discrete appearance. I can get 0. After 0, there is some smallest number I can get, okay, which is 7. That's the only number that can be, smallest number that can be written as a linear combination of integer linear combination of the two numbers, and then all multiples of that. Okay, so this is the situation if I started with two such numbers, whereas if I start with, say, 1 and root 2, then it's a very messy affair. So I start with 0, I know that the set S contains 1 for sure, it contains root 2 for sure, but then I ask, oh, what other numbers are there? Well, all integers are there for sure, all multiples of 1. Likewise, all multiples of root 2 are there, 2 root 2, 3 root 2, etc. But interestingly, all these remainders that we constructed, right, root 2 minus 1 powers, they are all numbers which live in this region, and in fact, if you actually plot the points of this set, you will find that there are many points in this interval, and in fact there is a whole sequence of points converging to 0. Okay, and I mean the same is true on the other side. Of course, similarly you will also get minuses of those guys are also in it, and so on. So this is a very, very different kind of set that you generate. So here's another nice problem for you to prove. So prove that this set that we constructed, so maybe problems 1, prove that S of 1 comma root 2, or more generally S of any two numbers, if I start with any two numbers P and Q, where P and Q are real numbers. Okay, so prove that S of 1 comma root 2 in particular is closed under addition and multiplication. Okay, so addition will of course be true with, if I pick any other pair of real numbers. Multiplication is sort of a bit special to things with square roots in them, 1 and root 2. So let's just do it in this example. Prove that the set of integer linear combinations of 1 and root 2 that we have been looking at so far, this is closed under addition, which means if I take two elements of this set, their sum is also in this set. Likewise, if two elements are in this set, their product is also in this set. Okay, so it's a very, very interesting kind of set. Okay, that it's got this sequence converging to 0, and in fact converging to any point in the set. Given any point in the set, you will be able to find a sequence from this set which converges to that point. and so that is maybe the second problem that I want to state. Given any element of the set, given let us call it P in the set S, prove that there exists a sequence, let us call it Sn, n greater than or equal to 1, with the following properties, that Sn, all the Sn's belong to the set S. So, when I say S, I just mean S of 1 comma root 2 here. So, let us do that again, 1 root 2 and limit of Sn equals P. Okay. In other words, not just for 0, see I showed that if I take 0, then there is a sequence converging to 0 from with elements of the set S itself, but not just 0, if I take any other point, if I take 1, I claim I can find a sequence of points from the set which converge to 1. Okay. Likewise, if I take, say, I do not know, 2 root 2 or 7 plus 3 root 2, I can find a sequence which converges. Okay. And the proof is easy, just use the first part. So, just think carefully about what the first part says, and you have already proved it for 0. So, now use that and the first part to construct a sequence. So, you do not need to start doing it from scratch again.